All right, line C4, learning task 2, identify possible cause of poor power quality. We left off in the last one after taking a look at a bunch of voltage characteristics, and I left off right at the point where we introduced harmonics, because all of a sudden I just was like, you know what, that deserves a completely separate video for us to go and talk about harmonics, because we hear about harmonics so many times. So rather than you have to search through videos to find it, we'll just put this one into its own video. Starting over there at figure 15, where we start talking about harmonics inside of a system. And harmonics themselves are going to go and just be multiples that we will have of our fundamental frequency. We're going to go and start by defining the frequency that we operate at normally as being my fundamental. Note how this thing has got an F over here that we are going to have. The frequency for us most of the time is going to go and be 60 hertz because we're working off of a 60 hertz system. In Europe, it would be a 50 hertz for their fundamental because they would be working off a 50 hertz system, etc. So for us, we're going to go and have a 60 hertz system as being our fundamental. We're going to go and call its sequencing positive. Sequencing is just going to be whether we are going to be going in a positive or a negative type of rotation. In this case, what we're talking about in a positive sequence is that these ones are going to be ones that are going to go and aid our regular type of rotation, and it's going to go and be a forward type of rotation that we would have. This is very critical that we note that we are on our fundamental. So what we mean to go and be at is at 60 hertz, and therefore we consider that to be a positive sequence with forward rotation. Our next harmonic that we're going to go and see up here is going to go and be our second order harmonic. So it's at number 2, so we just go 2 times 60, which gets to 120 hertz. That's going to become my second order harmonic. We would go and say that its sequence is going to go and be negative. It's going to be opposite to what we would have, and therefore as a result, it's going to try to go and drive any sort of loads into a reverse type of rotation. This is obviously going to be bad for us. If we've got a lot of harmonics on our system, those harmonics can start to counteract whatever is happening inside of motors and other components like that. So we don't go and say, this would be a good thing. We see that this thing is going to be trying to drive us in reverse. We don't want to go and have that. The third order harmonic that we are going to go and see is going to go and be this one over here. That's going to be what we would refer to as 180 hertz over here, third order harmonics, or triplen. You'll see that's one out there quite often. A third order is going to be anything that's a multiple of 3, 3, 6, 9th, etc. as we're going all the way through here. And those triplen harmonics are going to go and have a sequence of 0. In other words, they're not going to be helping us aid to go in the forward direction, nor they're going to be helping us to go and aid in the reverse direction. They're just going to be seen as being inert. They're just going to go and add on to what we have inside of our actual system. We're going to look at those individually later on. And then after that, we start going into our fourth order, which is then going to go positive or forward rotation, negative, 0. And what you need to be able to do is you need to be able to go and do this section mentally. The fundamental is going to be positive or forward. The next one up is going to go and be negative or reverse. And then we're going to go and have one that's going to be neutral. It's just going to add to it. See how it's 0, neither positive or negative. It's going to be a neutral one, which actually adds to the neutral. So we'll use that memory trick later on. Then we go back to positive, to negative, back to a neutral adding one, back to positive, back to negative, back to a neutral adding one like that. Which tells me things that are going to go and happen inside of the circuit. Let's start by taking a look at these positive ones. Now that we've laid out what the order is, these ones are going to go, and so we got this one over here, which causes actual work to go and be done inside of my circuit. These ones over here, my 4th and my 7th over here, and going on from there, you go up another 10, see how it's related by a factor of 10. You'd go on to 10, then you go on to 13th, etc. They're going to be rotating in the same direction. So what they're going to do is they're going to go and add onto our rotational forces. They're going to go and cause overheating inside of our windings and our supply conductors, because really what they're doing is they're adding to what we have inside of there. Just take it and look at absolutely anything where if you go and stuff additional current through it, even if it's current that's being self-generated, that current is going to go and cause more overheating. So these ones over here are going to be heating types. Let's put that up top over here. The next ones that we're going to go and have are going to be our negative sequence harmonics. That's going to be these ones that are going to be worked off of this. The second, go up by 3 to the fifth, go up by 3 to the eighth, etc. These are going to go and be reversing types of harmonics. Now, they do cause rotational issues that we are going to go and have. Usually, they're not going to be sufficient to the point that we're going to be able to actually have reverse rotation of a lot of our motors. But if I've got one very, very large motor, we'll draw a big motor here, and then we're going to draw a little baby motor over here. Maybe it's for a blower fan or something like that. The harmonics that are coming off of this one over here, anything that's going to be in these negative ones, they're second, fifth, and eighth, they're going to go and cause counter torques. So although my motor is trying to rotate like this, they're going to be creating these harmonics, negative sequence harmonics, that are going to be forcing back against it. My motor is still going to go and overcome it, but it's going to have to go and draw additional current in order to go and do so, which is going to go and cause, additional issues for my motor itself. The other problem is that these harmonics can go and escape back onto my conductors, and in some cases, the harmonics that I'm getting from this motor can escape back onto here, and they can get to this one, and they'll be sufficient that those harmonics are going to go and drive a smaller motor that's coupled onto the same system in a backwards rotation. Obviously, we would not want to go and have this, that is going to go and drive in a backwards rotation. So they can be really, really damaging as far as reversing is going to go, and they're going to go and cause heating once again as well. So these are going to be reversing and heating. And then the last ones that we are going to, going back to these ones here, these ones are going to come off of drives in a lot of cases, because we're going to go and have this switch down every time that we go through our 6-step drives where we've got, these voltages that we're going to be going on, then down, and back up, and then back up like that. That's going to be a 6-step drive over there. We're going to be collapsing these fields, and as we collapse these fields, we're driving current back through in the opposite direction, and any harmonics that come back off of it tends to go and cause, add onto these ones. So our older 6-step drives were really, really bad for giving us these type of harmonics, the negative sequence harmonics. 12-step drives are better. There's going to be more steps, more components that are going to be needed for it. We're able to eliminate some of them, the 5th and 7th, but we cannot get all the way back into our 11th and 13th. So we have got a limited amount that we can go and remove just by changing drive types. If you're having a lot of issues, remove the drive, replace it with a better drive, particularly if it's old enough that it's causing a lot of issues. It's time just to go and upgrade, put in a proper drive with a reactor right away. Past that, you're going to have to deal with filtering, sorting these things out and filtering what we have inside of the system. Triplet harmonics, or zero order or zero sequence harmonics, do neither cause more, positive rotation causing heating, or negative rotation causing, heating and rotational issues. These ones are going to be my zero sequence, which is going to go and cause issues on my neutral. They're going to be multiples of 3, 3rd, 9th, etc., 12. That we're going to go on from there. And these ones are going to go and cause distortion. We talked about this, at the end of the last video there, that if this was my fundamental waveform over here, and if I add that fundamental into that 180 hertz, this is going up and down, 3 times in the same time over there, we're going to go and get this double hump looking type of waveform over here. That double hump is going to go and have a couple of issues that we talked about once again before, but we'll bring them up one more time. First of all, we're going to have a low peak. That's never going to be good. We're not going to get up to high enough value of peak voltage. Secondly, because we are adding 2 waveforms over here, we end up with a steep edges. And steep edges are going to go and give us problems with, that says steep edges. Steep edges are going to give us problems with our DV, T, right? Delta V, delta T, or dVdt, right of rise of voltage over top of right of time that we are going to have, which is going to go and give us erratic triggering of electronic systems that we're going to go and have inside of there. We don't want to go and see that either. This waveform here, we're going to talk about testing for that one later on. The big issue with this one, once again, is also going to be that any of my neutrals that I'm going to go and have are going to be able to be counteracted, canceled, and I'm going to be able to go and feed neutral current back up and mathematically add it together. We gave that example in the previous video where we had 3 lines that were each pulling 10 amps, and that I could go and have, if I've got bad 3rd order harmonics, I can go and have a neutral current that is going to be anywhere between 0 all the way up to 30 amps that I would have directly off of it. Okay, let's talk about where we're going to go and get these things, the internal components that are going to go and cause these. We did talk really briefly about switching that we are going to go and have whenever we are going to go and look at a DC link. In the end of the other video as well, we dealt with this DC link, that the DC link only carries current for each one of these at a certain point. So I'm going to have my A phase there, then I have my A phase over here, which means that I'm going to have a current from my A phase, and then I'm going to go and have wait, and then I'm going to have current from my A phase. And so I'm going to have this imbalance one lead at a time that is going to be balancing through. And then once we have that cap that's inside there as well for filtering, then that capacitor is going to go and carry through some of it. And so it takes this and it pushes, instead of us having a current rise that's going to look like that, we're going to go and have a current rise that all of a sudden is going to go up like that and then back down. It makes it sharper edges off of these again. It's not going to be healthy for our system to go and take lots of pulses. It's obviously going to be, far better for this thing to have a smooth amount of current slowly rising in, slowly falling away, rather than this like bam, 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 bam sort of sequence that you're going to get off of currents otherwise. Okay, let's talk about issues inside of our system that are going to go and cause these harmonics. One of the harmonics that we're going to get is going to be off of phase voltage imbalance. And if I get phase voltage imbalance, it's going to go and change my magnitude of voltage that I'm going to go and have on any sort of given line. Oops, sorry, not that one there. We'll just use this slide over here. That's up top there. We'll erase some of this stuff. Phase voltage imbalance is pretty easy to go and describe when we're taking a look at a Y-type system over here. It's a little bit harder on the delta because we're going to go through two at the same time. But over here, if I take a look at my vectors that I would have for a Y-type of system, we know that V is going to be equal to I times R. And so if I go and take a single-phase load off of this and I connect it back to the neutral over here, what happens is I'm going to go and have additional amount of current that's going to be going through there, IR, which means I'm going to go and have additional amount of volts that I'm going to be dropping across my source. In effect, what this does, the single phase loads connected across there, is it skews this whole triangle so that this whole triangle becomes shorter on one side, the side that's got the single phase loads, and it is going to go and maintain its length on the other two there. You see how uneven this triangle looks as a result of these single phase loads inside of there. If I get voltage imbalances, this is going to be single phase loads, but the problem is that now if I've got a three-phase motor that is coming off of this same system over here, that three-phase motor is going to go and see these imbalance voltages. And as it sees those imbalance voltages, it is going to go and get a big push, and then a little push. They're magnetic pushes, but they're still little pushes that we're getting all the way around the stator. And we're going to go and get weird operation. The motor is going to kind of have a bit of a lurchy operation. It's going to sometimes have a different whine that you're going to go and hear to it. You're also going to go and get unwanted heat because this one here is so small it's not doing much, which means that this one and this one over here are going to have to do more than their share. They're going to have to pull along a little bit harder, which means that we are going to see more heat because they're pulling more current out of these things. Under our NEMA system, which is what our motors are going to be designed underneath for the most part, we do have IEC, but most of our motors are still NEMA. We're not supposed to be operating at voltage imbalances above 5%. So anytime that you have got large amounts of current that you're taking off just a single line like this, it would be better if instead of doing that, that you would break this load into three smaller parts. We'll make a baby load there, and then you would take another baby load, stick it across here, and another baby load, stick it across here. Split it up, put it evenly across your components. It's one of the last checks that you're supposed to be doing on a job site before you leave anyways, is just throwing your meter onto that job, onto that panel, and making sure all your phase currents are going to be somewhat the same. If I do get a delta system, delta systems, we can get these phase imbalances as well, particularly if we accidentally do that corner ground that we are going to go and have. Once again, if we got a corner ground that happens, inadvertently through a ground fault that happens on there, this and this corner both are going to go and rise to root 3 above ground levels, which is going to go and give us voltage imbalances, particularly if we have got any sort of Y-connected motors that are going across it. Because if we take a look at that, a Y-connected motor being fed from this, it would be like that's getting pulled across to here. I don't know if you remember those phase lights that we had for Delta at the beginning of the year, but your motor is going to go and act the same as we had for those phase lights. We're going to go and have, if I've got a Delta connected system that has got a corner ground on it, I am going to go and have my Y-connected motor, and we'll just pretend that that's the Y connection, that's the little center point over there. This is basically what my motor is going to be doing. It's going to be going across, from line to line like that, which means that these two phase sections are going to be stretched out immensely. Massive amounts of voltage over top of them, and they're going to have differing amounts of current that's going to go through them, and this as well is going to go and have a differing amount of current as it translates out of that line. It's just all around bad for these motors. Phase currents. We can go and imbalance the voltage through accidental grounds or through single phase loads as well. If I go and imbalance my loads, I'm also going to go and get that imbalance of currents. Basically the same thing, so we're not going to go and talk much about the phase current imbalance other than where we sometimes go and get these things from. They talk about that it gives us issues for circulating currents, excessive current in the neutral conductor because we're going to go and try to balance through our neutral if we've got a Y type. We'll get increased neutral to ground voltage and overheating of motors or insulation breakdown that's going to go and happen if we're pulling more current through one of our lines. Basically, anything that is going to go and happen inside of that list that you're seeing inside of your modules is all going to be caused off of the fact that we're going to have two that are picking up all the work and one that is not doing much. Anytime that we get a current imbalance, it's going to change the voltage, which is going to go and give us that unequal division of work. And that just really leads to burning out of the two overworked types of phases. It also leads to a lot of vibration, mechanical issues, because we're going to get big magnetic field, tiny magnetic field, and then big magnetic field, and then tiny magnetic field again. We don't like to go and see those types of operations because it causes mechanical things like bearings or imbalancing of our stators and stuff like that. We will get power quality issues off of a number of other things as well coming in here, where they're going to go through a few other last ones. Things like loose electrical connections. If we get cold flow under the aluminum where it heats up and then flows out from underneath points of pressure, that's why you're supposed to be retorquing your services. Faulty installations, particularly where you have ground loops, where you've got the neutral connected to ground in more than one location. Large motor startups, which are going to go and disturb. We're going to get, massive amounts of current that we're going to go and pull off of the system from inrush. And then this is a really big one for us, variable speed drives that we are going to go and have. VFDs, or adjustable speed drives for DC, or sometimes as we refer to them, soft starters as well. More specifically, it's going to be with our DC drives and our VFDs, because both of those follow that format where we are going to go and take AC in and then convert it to DC. And it's that AC converting to DC that gives us that big problem. And then when we take the DC, we can either feed it out as DC on a DC motor, or we can feed it out through an inverter as AC on there. What we will get is we will go and get weird operation from our current, because our current over here, we see that we've got no voltage, and we slam the voltage into a peak, and so I'm going to go and get an inrush of current that's going to go and happen over here. That inrush of current is then going to go and filter away as I charge this thing up, right? Anytime, if you go through DC, this is a DC voltage, a flatline type of voltage. We're going to go get that inrush of current that's going to go and start up. Our voltage is going to charge on that coil of our motor, which means that our current is basically going to be dropping away like that. That whole universal exponential curves that we've talked about before, we see that off of here. That's a universal exponential curve that we're seeing drop. Oop. And then when we go and shut the motor off, we're then going to go and have a discharge. That coil is going to go and discharge, so there's going to be a brief little flash of current, and then it's going to go and charge up in the opposite direction, etc. So we just get this current waveform that is a non-linear type of waveform. Once again, if we can go and filter what we have coming in, we can go and smooth out a lot of these drops and rises, and we can get more or less to the approximation of a proper sine wave through it. They list out a bunch of machines after this that do have high amounts of noise inside of here. We'll get to the power factor correction capacitors in a second, but machines that cause noise, arc welders, huge amounts of noise. You got to oversize your neutrals with those things and oversize your conductors, just because we're going to get such rapid, dirty power that's going to be happening inside there. Computer equipment, anything where we've got servers or large office buildings full of, just computers inside there. We've got a couple of them that are particularly bad that are going to go and deal with high voltage, where we're trying to go and ionize stuff inside of them. Copy machines are going to be big. Laser printers are going to be big as well. Microwaves are also going to be big. They're not listed inside here, but they provide a lot of dirty power. You've probably experienced that before. Your mom turns on the microwave or something, and then all of a sudden your phone or something cuts out. you'll hear these things, inside of different places where people are like, yeah, every time that I'm trying to go and work online, I get taken off every time that a microwave goes on. It's usually because people have got their routers way too close or things like that, but it's dirty power that's going through their residential system. Electronic ballasts are going to go and give us dirty power. Medical imaging, if it is a medical imaging place where we got CTs, X-rays, and things like that, it will be engineered. They should have proper filters in them, and most of these machines come properly filtered because they're so expensive. You don't want to be burning them out, but they cause a lot of dirty power. And then the other one that is not mentioned in here as well is going to be LED lights. We talked about that before, that peak repetitive stress that can really go and give us, weird current waveforms out of these things. All of those are going to give us bad power, dirty power, sometimes large harmonic currents that are going to go and be affected if we got switching power supplies like the computers and the electronic ballasts and things like that. Power factor correction capacitors, we generally get more transients that are going to go and happen inside of there, and then they're going to react to frequencies, harmonics that are caused by other things. If we do get harmonics that are caused by other components on our system, if they go back into our power factor correction capacitors, we can get some massive problems with overheating and puncturing on those, particularly if we accidentally drive these things into resonance or anything like that. The next part of your binder over here really starts talking about performing troubleshooting. Performing troubleshooting of power quality issues is horrendous. It is like one of my least favorite things to do out there because it's just so, it's so hard sometimes to go and track this stuff down, particularly if you don't want to go and spend, thousands and thousands of dollars on high-end equipment. In a lot of cases, you could rent good quality meters either through wholesalers or through rental places or from other companies, that will go and loan you stuff for either cash or a case of beer or whatever. But you are going to be able to hopefully get your hand onto some sort of a power quality analyzer. We're going to deal with those later on, but before you even start that, you have to start by just doing a walkthrough. A lot of it can be identified just by the load types and by the timings. Go through, get as much information as you can as to, first of all, what the issue is. Then try to develop an accurate one-line diagram of the entire thing. A one-line diagram is just going to go and show where you've got your incoming power. And then from there, you're going to go and take it down. You're going to do all of your sub-distributions. And then from your sub-distributions, you're going to go into your distributions outside of that into panels, etc. And usually you can start to, after a while, kind of clump where you're getting the most disturbance, less disturbance, and even the least disturbance across there. And then you can just kind of work your way backwards to try and find what it is. And then look at the types of machines that they have and if they're tied to time. If it's always happening every single day at the exact same time, then it's going to go and be probably something that's just timed when something else comes online. A friend of mine used to work for a company that dealt with, massive, expensive laser printers, like huge industrial units. And they had one where they just could not get this thing to go and stay on. And it turned out that it was to do with a photocopier 3 floors above owned by a different company. It was inside of a, multi-level commercial type of building. But they ended up having to trace it all the way back through the main panels, back up the sub-distribution, just by looking at the magnitude of the harmonic distortion that they were having inside of there. You do need to be there for a fairly long day. This is not a 5-minute, stop in or anything like that. You're going to want to watch, see what happens, see when stuff is, take measurements for like beginning of the shift, end of the shift, see when the heat is really starting to build on stuff, etc. And then talk to the people that are there. A lot of cases, the bosses are just going to hear that this machine doesn't work very well, and then they phone you and they say, come here, fix it, because I need it to work. If you talk to particularly like lead hands that are competent on the floor, those lead hands will usually be able to say, yeah, we didn't used to have this problem, but then we put this new machine in, or we changed this, and then we started seeing these problems. Then you can trace out from there. Start working at the service. If you have a system problem that's available, that has problems absolutely everywhere, you know that you're going to go and start then at the source. So if I know that I'm getting problems everywhere, I'll start over here. Then I'm going to go into each of these branches and I'm going to look for which one has the most problem, and then I'm going to start, working my way further back down into that. If I've got just a single load that is getting, really screwy characteristics out of it, then I'm going to start at that load and I'm going to start working my way back out and back up, because in some cases you're going to go and have, components that are going to go and be operating almost inside of like a vars type of bubble. It's harmonics, it's not vars, but the same type of thing where I've got this load over here that is not, operating correctly, and I can trace that thing back up, and I can trace that thing all the way back up to here because I know that these are fine over here, and so you're just kind of tracing from there, looking for where you're getting more distortion off of the system. All of this stuff is going to be done through the use of proper meters, hopefully. Particularly, you're going to be monitoring what's called THD, which is total harmonic distortion that we are going to go and have on a system. THD is going to be a measurement of the amount of junk on our system. It doesn't show us this picture of the system because we don't necessarily know what to do with that, but it's going to go and tell us, hey, we've got distortion, you got a lot of distortion around, this frequency or this frequency or this frequency, and then you can also try to filter some of that stuff back out. You should be using a good meter for all of this tracing and locating. Particularly, you need to be using a meter that is going to be true RMS. If your meter is not a true RMS, which means root mean square, you're not going to be able to do basic checks on it. You're also going to need to make sure that your meter is going to be rated for the proper category, right? The closer you are out towards the main service, the higher the category rating needs to be because there's a greater chance that you're going to be exposed to massive faults on the system itself. One of the simplest checks that you can go and do is to go and look for this thing that's going to be called Crest Factor. And a Crest Factor is really just going to be taking a look at the RMS versus the peak. If I have got a proper AC sine wave, let's draw one out right over here. We know that on a proper AC sine wave, we have got an RMS value of 120 volts. But we also know that we've got a peak of 169.8. We usually round that thing out to 170 volts. And we know that the relationship between this and this is going to be the inverse of 0.707 or 1.414, right? Take 120, multiply by 1.414, you get up to 170, or vice versa, or take 120 and you can just divide it by 0.707. That'll get you to the same values. This is going to be important that we remember this, that our value between V peak over to V RMS, because if we've got a good waveform, we should have this ratio that is going to go and be maintained. If I don't have a good ratio that's going to be maintained, let's go to that, third order harmonics. Under third order harmonics, I can still sometimes get 120 volts RMS, but what I'm getting it off of is I'm getting it off of this steep-sided double hump wave that's going to be over here. Looking like that. If I go and measure this peak over here, that's not going to be at 170. I'm going to be looking at, let's say 150. And all I would be doing is I would be saying 150 divided by 120. Is that going to be equal to 1.414? And then if it's, not equal to, or if it is equal to, that's going to tell me whether or not I've got an issue. I am looking for that 1.414. Now, in some cases, if you don't have a good quality meter, it's going to be difficult to go and do this. You're also going to have to do this while the system is live, measure these voltages. We're allowed to measure voltages live. It's one of the things we are allowed to go and do. But you're just going to have to be careful, use proper PPE and everything else as part of that. Some cases you won't necessarily see it on the voltage, you will otherwise see it on the current. Remember that harmonics can be either harmonic voltages or harmonic currents. So if you measure with the volts and you get a good crest factor, the next thing that you should be doing is you should be going and taking a look at this thing as far as currents is going to go and do. To do that, you're going to go and have to use, once again, a set of clamp-on ammeters that we're going to have in this case, so a meter. We're going to go and take one that's going to go and take an averaging, the other one that's going to go and take true RMS. And this is going to go and once again give us a crest factor that we would need to go and have. If we're not getting that crest factor, then we've got problems with these ones. So yeah, you need peak on your meter. If you don't have a good meter, the stuff that you should be looking for on that one, if it can do crest factor alone, that's great, but you want to have true RMS and you need to go and have a peak hold that is going to be part of it, as well as you want to have the smallest sampling time, where it's going to go and just grab this, be able to see a whole waveform. Some of them only take a couple samples, in a second type of idea, which is going to be really hard to get a good average off of. You want to have a high sample rate inside of these. Okay, yeah, I think that's as far as we want to take this one over here with the crest factor and all that other stuff. When you're going through, you're going to go and check voltages, you're going to go and check currents, you're going to be, making sure everything is balanced. As soon as you get an unbalanced voltage or an unbalanced current, then you are going to have to go and, stop and say, is this going to be acceptable down here? Once again, working off that one line, if you have at the source a balanced voltage and then all of a sudden you get, like 2 or 3 sub-distributions down and you're starting to see unbalance, it's going to be something on that system that's obviously causing that imbalance. You want to keep everything up to about a 1% for your voltage balance. Voltage should stay the same across all components. So, it should be 120, maybe it might be 119, and then you might have another one that's, 121 or something like that. That's fine, that's 1%. Current is going to be more unbalanced, and so we allow imbalances of up to about 10% that we are going to go and have. Neutral overloading. On receptacle branch circuits, we can sometimes go and check if we've got an overloaded neutral just by checking if we are dropping voltage across the neutral. The neutral itself should be dropping next to no voltage across it. We know that we have got a neutral that will be connected over to ground. So if I take a look, I'm going to have my hot line, and then I'm going to go and have my bond slot over there. What I can do is if I have got something else that is operational, so I've got a set of receptacle circuits over here. We'll just put this one in up top over there. And I've got a load that is connected into this one here right now. What I can do is I can go and check what I have got for voltage going across from my neutral. That's going to be the big slot over to my bond that I'm going to have over here. There should be, we're not checking continuity, there should be a small amount of voltage drop because all of that current does still have to travel down the neutral over to my supply and back. If I am going to be higher than, about that 2 to 5 volt range inside of there, usually that's a sign that we are dropping a lot of volts across our neutral, which is going to be a sign of harmonics that we are going to go and have on there. As far as instruments that we're going to use, they list off a couple of instruments. Handheld oscilloscopes, really handy. Temperature guns, super, super handy for taking measurements. Oscilloscopes are very expensive. They're also getting a lot more accessible. If you work off of a laptop at any point, I work off of a laptop, and what you should have is you should have just a little black box oscilloscope. Most of the cost inside of an oscilloscope is going to be the software that processes and displays the graphics, as well as in the screen and all the push buttons that you would have, push buttons, knobs, etc. What we have in a lot of cases, and they're becoming really popular out there, is we're going to have one that's going to be USB connected to your computer. It's going to be optically isolated, so you cannot go and pass any sort of a surge along into your laptop, but then you're going to go and have 4 or 8 channels that you're going to go and have off of this. They're just going to come into this black box. They're going to be B and C connectors inside of there, and then you just run the manufacturer's program on your laptop. And as you run that manufacturer's program, then it's just going to go and read all of this, put it up on a screen. You can make all of your adjustments digitally on that screen. I highly suggest that, once you get into, particularly you're into industrial type of stuff, first of all, it buys you time. If you're not sure what's going on, you just pull out your oscilloscope, you put that oscilloscope on, and you stick on a couple different colors on the graph lines, and you just tell your customer that right now you're putting that onto monitoring mode, you're tracking some other stuff. They just feel good about that because there's blinky lights and colors. You might not have any clue what you're doing yet, but it's going to buy you some time because they're going to be fascinated by watching their voltage for a little bit, and they don't understand it anyway, so you're fine to, go out there. I'm not saying go out there and purposely try to bamboozle these guys. I'm just saying it's really handy when you're in a high pressure situation to have something that they don't understand but that looks cool because it keeps them off your back for a couple more minutes while you try to sort out what exactly might be going on. Infrared thermometers, very handy for taking non-contact measurements. Obviously, you can't just go touching stuff inside of components, so we will use these to measure out anything that we have going on. Always start by taking a reference reading. A reference reading is going to be inside of the same enclosure. You don't want to do it outside the enclosure. What you want to do is you want to go and just shoot the back wall of the enclosure from about the same distance that you're going to go and shoot over to the lugs that you want to check, etc. Usually about 8 to 10 inches away. So you're going to shoot the back wall, take a note of that measurement. Then you're going to go and shoot each of the individual components that you want to go and test, and your components should be roughly the same as the enclosure. If they're way hotter than the enclosure, you know that they're the source of heat that's going to be inside there, and if that heat is on lugs and conductors, once again it helps you to track down that you've got harmonics that are going to be on it. These are simple checks. You know, the oscilloscope, the temperature meter, the Crest Factor, all of that is going to be simple checks that you can do that'll tell you that there's some problems, but they're not going to necessarily solve it, nor are they going to tell you a lot about that. That's going to be the next learning task we're going to look at going into solving these things using our power quality analyzers. Last couple sheets that they have over here are going to be troubleshooting guides for load problems versus distribution problems. The first one over here talks about what the loads are and what problem you see, what it is, what the pattern is, if it has a pattern, doesn't have a pattern, if it's got problems with this thing before, possible problems, measurements taken at load. You're going to go and do all of those type of things, waveform, shape, measurements taken over time, etc. So this is the type of thing where if you have a customer that has a load that's causing problems, you come in, you show up, you don't know a whole lot about what is going on, and you don't have an exact answer at this point. What you'll do is you'll leave them with something like this, and then you tell them to go and monitor that. When does it happen? Every time it happens, log this, write this down, and tell me what's happening with it, and then that gives you a little bit of time to come back and sort that data with them. If it's happening rhythmically, what else is happening rhythmically inside that plant? If it's going to be an actual overall system that I'm seeing, then I'm going to go and deal with something like this. Different. The other one was based upon a specific type of load. This is now going to be off of the entire system itself. Once again, what the problem is going to be very, very important to you, as well as the patterns. Patterning. Once you get that figured out, it's going to go and work out in your benefit. All the rest of these yes, no questions that are going to be here, you're going to go through and just write down the data and use it to, once again, track down what is happening inside of here. Last one that they have is a sheet for facility transformers and main service equipment problems. So just a little bit further out than the other. This one's basically the same as the previous one. Once again, same stuff that you're going to be looking your way through. Okay, that covers us through the causes of poor power quality. It's a difficult thing to track down. Just be prepared that in the field you are going to struggle with this. There are experts out there that are going to be able to come in and tell you things and sort stuff out. If you're really struggling a lot, don't be afraid to go and tell whoever your customer is that, look, this over here is outside the scope of what we do. We build, we maintain, etc. But tracking this stuff down, you've got power quality issues, let me hook you up with somebody who's going to come in. And as long as you make sure you talk with these guys first, that some of these companies, they want to supply the equipment. If they do the analysis, they want to be the ones to supply the equipment. Just make sure that you're talking to them and sorting out details like who's going to do the installation, etc. Lots of guys out there have been burned off. They'll get a power quality company to come in and take a look. The power quality company is going to go and make some recommendations, but then they install it onto that system as well. It just cuts you out of making some of your profit that you might have, but more importantly, might not be up to your same standard. It's better for them to, if you're the site electrician, you deal with that install, you just get them to go and take the readings, provide the equipment, you hook it up, and then they commission it. Okay.